When designing wireless networks, both coverage and capacity requirements must be considered. When designing for coverage, radio frequency, transmit power, antenna type, positioning, interference, environment can all impact signal propagation. Site survey software with planning capability like Ekahau, AirMagnet, and Tamograph can be used to model RF environments. Let's use an American football field as an example. It's 100 yards or 300 feet from end zone to end zone. If an access point was placed at one end of the end zone, how far do you think the signal would go where we would still see a neg 67 dBm reading? This will be a generic omnidirectional antenna, AP mounted 8 feet high, and a transmit power not 100 milliwatts or 50 milliwatts, but let's set it at 10 milliwatts. I'm using Ekahau Site Survey Pro, which includes planning software to demonstrate how far RF travels in free space. When using programs like Ekahau, the first task is to open the floor plan of a site drawing, and then scale the drawing. I'll select a scale tool, and then I'll click end zone to end zone, and we know that's 300 feet, so just 300. So now we're good. We have the visualization legend set to display neg 67 dBm or better, and we'll leave the cutout value at neg 80 dBm. We want to simulate an access point, and you can see Ekahau lets you model a number of APs from different vendors. Let's use a generic Omni 802.11ac AP, and we'll place it at one of the end zones. You can see that this AP provides neg 67 dBm coverage or better in free space. We're looking at 2.4 GHz coverage. Let's choose 5 GHz coverage only, and you can see it covers all the way to the end zone. But let's verify the AP settings. We'll edit to 2.4 GHz radio, and let's change that from 50 milliwatts, and I said let's set it down to 10, right? And the same way for the 5 GHz radio. We'll change it to 10. And both the 2.4 and the 5 GHz radio, note that they're mounted about 8 feet high. Now we can clearly see the neg 67 dBm coverage. This is the 2.4 GHz coverage. There's 5 GHz. So here you can see at the same power level, 5 GHz doesn't travel as far as 2.4. Now let's look at the effect of drawing one wall. Normally with programs like this, you're opening floor plans and you're defining wall types with modeling. So I have the wall tool selected, and we can see that there's different wall materials. I'm going to draw a drywall type of wall, and we'll draw the wall around the 10-yard line. So here we see the impact of the wall with the 2.4 radio. Let's undo that. So no wall, and then the wall. Let's look at 5 GHz with the wall, and then I'll put it back to 2.4. Now imagine that you design with walls as drywall, and after deployment you learned that it was concrete walls in one building. Let's change the wall type to concrete. So I'll just select the wall, right click, change wall type, and we'll choose concrete. So you can see it's a big difference with concrete, isn't it? This is 2.4 concrete. Let me undo it. That's 2.4 drywall. Let's put it back to concrete. Now let's look at the impact of 5 gig. That's 5 gigahertz with concrete. And then there's 2.4. Big difference, right? In this demonstration, we illustrated that RF can travel a good distance in free space and the impact of wall material. In another demo, we'll look at modeling an office building.